Hey everyone, today we're tackling a Leetcode problem called put marbles in bags. It sounds simple, but there's a clever trick involved. Don't worry, we'll break it down step by step. Alright, so what's the goal here? We have a bunch of marbles, each with a weight. We need to divide them into a specific number of bags, let's say bags. The key rule is, if you put marbles from index to in a bag, you have to include all the marbles in between them too. You can't skip any. The kinpur of a bag is just the weight of the first marble, plus the weight of the last marble in that bag. Our overall for a particular way of dividing the marbles is the sum of the costs of all the bags. The final answer we need is the difference between the highest possible score we can get and the lowest possible score. Let's walk through the first example. We have weights 1, 3, 5, 1, and we need to make two bags, k equals 2. How can we split this? Remember, adjacent marbles must stay together. We can split between marbles. To get two bags, we need just one split. Where can we split? 1. Between 1 and 3 gives bags 1 and 3, 5, 1. Cost of 1 is 1 plus 1 equals 2. Cost of 3, 5, 1 is 3 plus 1 equals 4. Total score equals 2 plus 4 equals 6. 2. Between 3 and 5 gives bags 1, 3, and 5, 1. Cost of 1, 3 is 1 plus 3 equals 4. Cost of 5, 1 is 5 plus 1 equals 6. Total score equals 4 plus 6 equals 10. 3. Between 5 and 1 gives bags 1, 3, 5, and 1. Cost of 1, 3, 5 is 1 plus 5 equals 6. Cost of 1 is 1 plus 1 equals 2. Total score equals 6 plus 2 equals 8. Comparing the scores 6, 10, and 8, the minimum is 6, the maximum is 10. The difference is 10 minus 6 equals 4. That's our answer. So the first idea might be, okay, let's just figure out all the ways we can possibly divide the marbles into bags, calculate the score for every single way, and then find the biggest and smallest score. But how many ways are there? If we have lots of marbles, the number of ways to split them could be huge. This sounds like it might be too slow, especially for larger inputs. We probably need a smarter approach. Let's think about what determines the score. To get bags, we need to make exactly cuts or splits between adjacent marbles. Imagine our weights are W1, W2, W3, W4, W5. If we need k equals 3 bags, we need two splits. Maybe we split after W2 and after W4. Bags, W1, W2, W3, W4, costs, W1 plus W2, W3 plus W4, W5 plus W5. Total score equals W1 plus W2 plus W3 plus W4 plus W5 plus W5. Let's look closer. What if we split after W1 and W3? Bags, W1, W2, W3, W5, costs, W1 plus W1, W2 plus W3, W4 plus W5. Total score equals W1 plus W1 plus W2 plus W3 plus W4 plus W5. Notice something interesting? The very first weight, W1, and the very last weight, W5, always contribute to the score. W1 is the start of the first bag, W5 is the end of the last bag. What about the weights at the split points? If we split between where and where plus 1, then where becomes the end of one bag, and where plus 1 becomes the start of the next bag. So both y and y plus 1 get added to the total score at that split point. Okay, here's the crucial realization. The total score for any valid division into bags can be calculated like this. Take the first marble's weight, add the last marble's weight, and then, for each of the places where you made a split, say, between marble I and marble I plus 1, add the sum weights plus 1. Think about it. The first weights, 0, and the last weights, 1, are always part of the score, no matter where you make the splits. So when we calculate the difference between the maximum possible score and the minimum possible score, these two constant values will just cancel each other out. This means the difference only depends on the sums of adjacent pairs, weights plus 1, that correspond to the split points. We need to make K1 splits. To get the maximum score, we should choose the K1 split points that have the largest adjacent pair sums. To get the minimum score, we choose the K1 split points with the smallest adjacent pair sums. So the strategy becomes much simpler. First, go through the weights and calculate the sum for every adjacent pair. Weight 0 plus weight 1, weight 1 plus weight 2, weight 2 plus weight 3, and so on, until the second to last plus last. There will be such sums if there are marbles. Second, put all these sums into a list. Third, sort this list of sums from smallest to largest. Fourth, to find the minimum score contribution, just add up the first K1 sums from the sorted list, the smallest ones. Fifth, to find the maximum score contribution, add up the last K1 sums from the sorted list, the largest ones. Finally, subtract the minimum sum from the maximum sum. That's our answer. Remember, the weights, 0 and weights, 1 parts, cancelled out. Okay, here's the Python code that implements our strategy. It might look a bit dense at first, but it directly follows the steps we just discussed. We'll break down the key parts next. First, we get the number of marbles. There's a quick check. If is 1, just one big bag, or is each marble in its own bag, there's only one way to do it. So the max and min scores are the same, and the difference is 0. We can just return 0 right away. Otherwise, we create an empty list called split_costs. We then loop from the first marble up to the second to last marble. In each step, we add the current marble's weight, weights, and the next marble's weight, weights plus 1, together, and append this sum to our split_costs list. This list now holds the costs associated with splitting at each possible point. Next, the crucial step, we sort the split_costs list. This puts the smallest potential split costs at the beginning and the largest at the end. Then, we calculate the minimum possible contribution from splits. We need K1 splits for K bags. So we loop K1 times and add up the first K1 elements from our sorted split_costs list. These are the smallest ones. Similarly, we calculate the maximum contribution. We again loop K1 times, but this time we add up the last K1 elements from the sorted list. The code split_costs 2y might look a little tricky, but it's just accessing the elements from the end of the list inwards, the largest, then second largest, and so on for K1 elements. Finally, as we figured out earlier, the weights 0 and weights 1 terms appear in both the maximum total score and the minimum total score. When we subtract the minimum from the maximum, these terms cancel out. So the final difference is simply the sum of the largest K1 split costs, max_score_splits, minus the sum of the smallest K1 split costs, min_score_splits. We return this difference. So how efficient is this approach? Let's look at time. Calculating the adjacent pair sums takes time proportional to the number of marbles, n, that's roughly order n. Sorting these n1 sums is usually the most time-consuming part, taking about order n log n time. Then, summing the smallest and largest K1 elements takes time proportional to k, which is at most n, so that's also order n. The dominant factor is the sorting, so the total time complexity is about O(n) log n. This is much faster than trying all combinations. For space, we need to store the n1 pair sums, which takes order n space. The sorting algorithm might also use some extra space, often up to oxygen mononitride as well. So the space complexity is roughly oxygen mononitride. Alright, let's recap the main ideas. The big win here was transforming the problem. Instead of thinking about forming bags, we focused on the K1 splits we needed to make between marbles. We realized the difference in scores boils down to choosing the K1 cheapest versus the K1 most expensive splits, where the cost of a split between index I and I plus 1 is simply weights plus 1. By calculating all these potential split costs, sorting them, and then summing the smallest K1 and the largest K1, we could find the difference efficiently. And remember that the first and last marble weights don't affect the final difference. Hope this explanation helped you understand the put marbles in bags problem. It's a nice example of how rethinking the problem structure can lead to a much simpler and faster solution. If you found this helpful, please consider liking, subscribing, and leaving a comment. And hey, if you're feeling generous, you can support the channel at buymeaboba.com. Happy coding, and see you next time.